Okay, hello everybody. Welcome back to, I guess, technically the third lecture of numerical algebraic geometry, where we get to do some live coding, which means you will see mistakes in real time. And we will work through them. And if they're particularly disastrous, maybe I'll pause the recording. But in general, I would like to advertise the fact that mistakes happen and you can actually read the error messages and try to suss out what's going on. Okay. So in this course, we are going to be using Julia. Julia is a programming language. And in particular, within Julia, we will be using a package called homotopy continuation.jl. Okay. If you want to try to follow along, great. Especially if you're online, it's going to be much easier for you to follow along because you can pause things, go back, etc. Make sure things are appropriately downloaded and all that stuff. Okay. So we're just going to do our best to get to a crash course. If we're lucky, we are going to compute the 27 lines on a cubic surface. That would be amazing if we could do that in the first class. No promises. So here we go. So I'll share my screen. All right. So I'm running Linux. If you run Windows, you can use the WSL Windows subsystem for Linux. And apparently this makes it incredibly easy to download Linux software and to use it. Let's chat in the Discord server if you have problems. So we have people in this class who've done this. If you're running Linux, congratulations, your life just got a lot easier. There are some links on the website on how to download Julia and how to add the package and all that stuff. If you prefer working with a so-called IDE, so some sort of development tool for code, great. In this class, we're going to keep it really bare bones. On the right, I'm going to have a text file where I'm going to copy and paste code that actually worked so I can post it to the website so that we can all have copies of the sessions that we're doing in this course. And on the left, we're going to actually type that code into just a terminal window, okay? So if you want to know whether or not you got Julia running, you go to your terminal. By the way, my computer's name is Salmon, not for the fish that you get as a prize if you solve a problem, but for the mathematician. Okay, and if you zoomed in too much, you don't get the pretty splash screen, but yeah, it looks like Julia right there. Okay. Okay, so Julia, bare bones, I can add numbers. Okay, I can write functions. Function, my plus AB, C equals A plus B, return C. Okay, we don't got to deal with any of this semicolon business, all right? We don't got to deal with any of this typing, right? I don't have to tell them A is an integer or anything like that. Julia is very forgiving. That's great because you can rapid prototype a bunch of software. A lot of times when you're working with a very forgiving programming language, this comes at the cost of performance. That is not the case with Julia. So as soon as you write something like a function like this, now that it's working, then I can go back and I put types and everything, and this will optimize the speed of this code. Julia is a performance language. Okay, so now I can do my plus of 2 and 3. Yeah, great, 5. My plus of, let's see if I can do this. So vectors, lists, arrays. Okay, we put them in between these square brackets. Yeah, great. So it kind of knew that there was a plus associated to the data type that I put in. Okay. So that's what I mean by it's forgiving. This is not a plus function just for numbers. Okay. It will check whether or not, yeah. Strings. Can I add strings? Good question. Hi, Rajwal. Nope, no method matching plus string. String concatenation, and it's so helpful. String concatenation, which is probably what you meant to do, is done this way, silly. So hi, Taylor. Oh, there we go. String concatenation. Okay. We're not going to be dealing too much with strings. But good question. Okay, great. So maybe I want to get a matrix. So 1, 2, 3. 1, 2. Well, let's try. I always forget how to do this. Oh, there it is. Spaces for the rows, semicolons for the new rows. Okay. Let's get a square one and try to take its determinant, eh? Oops, determinant's not defined. Maybe it's determinant. No. Okay. By the way, almost all functions in Julia are lowercase. Okay. With underscores in exchange for spaces, and not camel cased. So yeah, uppercase things are meant for like data types, like I guess type of matrix. Matrix is capital. So if I ever have an object that I'm working with, and I'm like, okay, well, like, what does Julia think this thing is? I can say type of. That's a really helpful debugging tool. And then like, maybe I'm like, okay, well, what can I do with that type? Methods with. Oh, by the way, okay, what I just did was I started typing something and then I hit tab twice. It will tell me all the things it knows that start that way, right? So I did methods, tab twice. If there's only one choice and I hit tab, it'll auto-complete. This is gonna make you very fast if you start doing it now. Okay, methods with what? Oh, maybe a type of this matrix. Okay, can't do anything with the matrix.
It stores it as a
because it thinks the matrix, so the matrix has a specific type, so it's a parameterized type, right? So we have matrices as mathematical objects, but inside the matrices they have entries, and those entries have a type, right? So this is telling me that it's a matrix with integers as the stuff inside. So anything I can do with integers, I can do with the entries of this matrix. It's great. Yeah, and so there are all these things I can do. Set in, okay, mysterious, but it looks like there are 14 things Julia thinks I can do with the matrix. Well, I bet I could do a lot more if I had a package that did linear algebra for me. I bet I could take a determinant. Indeed, like what is a math software that can't take a determinant? You know, not super great. So so how do I do this? So first of all, there are two ways to kind of interact in this terminal window. And the first one is how I've been doing. I've just been typing in, and I get this green font that says Julia next to it. I'm putting in Julia input. Okay, but now what I'm going to do is I'm going to type this character. Okay, that's a closed bracket. Let me see if I can zoom up this. Fonts and colors, blah, blah, blah. Quick brown fox jumps over to something. Okay, there we go. Okay, that character. So in the United States, we would just call this a bracket, but apparently parentheses are also called brackets here. So square bracket. Okay. So let's see what happens when I type that. Boom. Okay. So now it's saying the version of Julia I'm using, and PKG stands for package. This is my package manager. If I want to get out, I type backspace, bracket, backspace, bracket, backspace. Well, what the heck can I do in the package manager? I can manage packages. So let's see what the status is of what packages I've already managed before I've walked into this classroom. I type ST for status. I type enter. And here you go. So on my computer, there is a project.toml file, which has the information of the following, say, 15 packages. Okay. And their versions. And I can like update them, blah, 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 whatever. If you've just downloaded Julia, this should be essentially empty. So let's add a package. The command for that is add, followed by the package name. So I'm going to start typing lini and then type tab. So I hit tab twice. Here are all the packages that Julia knows about that starts with line. Okay, so I type some more. Linear. Okay, a lot of things that start with line start with linear. Great. Linear A. Okay, great. Linear adjoints, linear algebra X, linear algebraic representation, and linear algebra. Give you one guess on which one we're going to use. Linear algebra. If you want symbolic linear algebra, as distinct from numerical, Linear algebra X, I believe, is your go-to. Okay, great. So now I got, now I type ST. So it said, okay, we're going to update the registry, resolving the package version. So Julia is very smart. So if I want to work with a bunch of different packages, which are developed by different people, I put them, you know, I add them all in this way, but then all those packages have dependencies, right? And this needs to be resolved in some sense, right? So maybe, you know, Alex's package uses linear algebra's this version, but Mac's package uses linear algebra this version, right? So it's going to find the version in that version tree, which will make both work. Or it'll complain that, like, I can't make everything work. I'm so sorry. Okay, so that's what it's doing when it's resolving package versions. Okay, so that's incredible that it does this, this management for you. It's incredible if you're a mathematician proving theorems, because when you write your code and you publish your paper, you can write down this list, which will tell somebody exactly which versions were put together to make the code run. If you have worked in computational mathematics before, you know that a lot of times math software just dies because somebody didn't update it with respect to this new linear algebra package that people are using or something like that. The version control doesn't work. Or somebody leaves academia and, like, it's completely lost, right? So this is going to handle version control for you. All right, so now maybe I can take the determinant. No, because just because my computer knows about linear algebra doesn't mean I've told my computer to load up all that functionality. If every time I started Julia, I loaded up all this functionality, it would take me an hour to start Julia every time I ran it. So this is a feature, not a bug. Okay. So using linear algebra. Hey, awesome. Great. Now I have a determinant. Yeah. Okay. So I'm going to try to teach you just some more little tricks that'll help you debug things on your own. Okay. So just like if we type close bracket, we go into the package manager. If we type question mark, we go into help. So I could ask for help about this det function. Det of m, matrix determinant. See also log det, log abs det. Here's an example. This is your bread and butter for learning Julia and learning all the functionality and the packages that we're using. If the documentation is good, you don't have to read a book on Julia, you read the documentation as needed. Well, what else does linear algebra do? So linear algebra, as soon as I load it, I have access to all these functions. But there are also maybe like some hidden functions that linear algebra is like using internally that I might want to like use. Or I might just want like a list of functions that I can use from linear algebra. So I would type the package name and then a dot. And then if I tab twice, I'm just going to get every function here in the package. Okay, so linear algebra is a vast world. So as expected, you have a lot of functions. Okay. But of course, if I, you know, rank maybe. Okay, so if I start like with ran and I double tap. Yeah, okay, well, how about just R? Okay. It'll tell me all the functions that start with R. Okay. Really helpful. Okay. And then of course, if I want to know anything about it, question mark and tell me how to do it. Compute the rank of a matrix by counting how many singular values have magnitude greater than some tolerance. Okay. So this is a numerical rank function. Okay. Questions so far? So go ahead and add this this package if you're following along. Homotopy continuation. And I'll do like a using homotopy continuation using algebra. Okay. Homotopy continuation. The newest numerical algebraic geometry software that I'm aware of, developed by Saksa Timma and Paul Breiting over in Germany. It's got a very fast and easy to use homotopy continuation. engine, okay? Here we go. So at this point, if you've added it, it's doing a bunch of stuff and you're waiting and you're just gonna have to sacrifice following along for the sake of time here. So let's get a little bit bigger. All right, let's solve that polynomial system, the intersection of the circle and the parabola. Okay. So let's just try to write the equation of a circle. See what happens. Okay. Oop, it's an error. Undefined variable error. X is not defined. So there's this amazing thing where it'll give you errors, and it really actually does help to read that. Okay, it tells you an idea of what's going on. If you want X to be a variable, you do that. Or you do that. Now you got X and Y. If you want, maybe you want like Z1 through Z15. You would do that. Okay. Or maybe you don't just want a one-dimensional array of variables because you're really thinking about 15 by 3 matrices. Do that. But for now, it's X and Y. All right, so then one of the main data types in homotopy continuation.jl is a system. And in the system, you put a list of polynomials. So yeah, x squared plus y squared minus 1, x squared minus 5. Okay. Good. And function. So system is a data type. That's why system got capitalized. It's not a function, right? We're constructing the system with this input. Solve is a function, not a data. Verbs versus nouns is a good clue. Verbs are lowercase, nouns are structures or data types. So now we'll solve it, and it'll take forever. And you go, Taylor, oh my gosh, you said this was state-of-the-art numerical algebraic geometry software. I could do this by hand by mouth. What you are waiting for is not the solving of this polynomial system. What you're waiting for is the compilation of several functions involved in solving this polynomial system. Unlike other programming languages, a bunch of functions are compiled just when they're needed. Okay. Again, this helps so you don't have to wait an hour to see these packages load. Okay, it's a feature, not a bug. But as soon as we call it, now those functions are compiled and it shouldn't take very long at all to solve. Wow, amazing. This all smells like the stuff I talked about on Tuesday, right? How many paths did you track? You tracked 4. How many non-singular solutions are there? Singular means bad, okay, for now. 4. How many were real? 2. Oh, that's exactly the picture Taylor drew on the board. How many singular endpoints? None. How many singular real endpoints? None. How many total solutions? 4. How many real ones? 2. And the data type that pops out is something called the result. Now, at the beginning of your numerical algebraic geometry life, this will annoy you that the data type is a result, because what you really want are the solutions. Well, you can just ask for the solutions. Okay. There you go. Take a look. So here's our solutions. So by the way, whenever you have a list of things, you can index elements of that list by these brackets. We index at 1 in Julia, not 0.
Yeah, that's a different one.
That is a feature, not a bug. I will die on that hill.
Can we pull the real solutions out of this?
Oh yeah, maybe. Okay. Okay. I've never used this before. Can I pull the real solution? So let me type real tab. Oh, that okay. There's something called real solutions. Let's do a question mark to see if we know how to deal with it. Oh, I just do real solutions of the thing that's outputted by solve. Wow. Okay. Let's compare. So if I ask for the real solutions, they're giving me vectors, so a list of things. Vectors of what? Vectors of vectors, right? Because each point itself is a vector, right? And if it's real, and we already know it's real, then what out pops are floating point numbers. Think decimals. But if we ask for the solutions, then it doesn't know if they're real or not. Maybe they're not. And so it's giving it to us as a complex data type. Awesome. Let's take a look at these complex numbers a little bit more closely, eh? Cool, so this first one's actually pretty interesting. The x value is on the imaginary axis. I'm not going to think too hard about why that's the case. The second one's real. This one's real, yeah?
Yeah, there are reflections about the y-axis.
Yes.
Plus minus.
Very good. That's right. Thank you. Okay, so this one's real. And you might be convinced over here that this is a real number inside this complex plane because it's a real part plus 0 times an imaginary part. But if you're not really familiar with working with numerical stuff, this might give you some concern. You're like, hey, wait, this looks like there is an imaginary part. No, that e to the negative 35 is e to the negative 35. It's so small. All right, it's like 0.00, right? So, so this is a feature of numerical computations, is that you're going to get really small numbers and you're not going to know whether or not they're 0. Right now, the best you can do is kind of look at it and be like, that's like super small. I bet that's 0. Okay. But if we want to certify these things, we'll use certification methods, which we'll talk about in the last chapter of this course, how they work. Knowing how things work is a lot different than using them. Using things is easy. I can just certify that S are solutions to F. Now, we have no idea what this is going to do because we haven't finished the course yet. And we have no idea what the output means yet, but we can use it. And maybe we can ask for the question mark of certify, get the help documentation. Maybe that suggests us to further readings, etc. Blah, blah, blah. Wow, great. Certifying 4 solutions, whatever that means. It's processed 4. It's certified 4. 2 of them are real. They're all distinct, and the real ones are 2 distinct ones. Great, cool. Okay, so I promise this corresponds to some rigorous mathematical result that we've just proven. Okay. Questions so far?
Are those paths tracked when we look at them? Like the paths tracked. What does it mean?
So do you remember the homotopia I talked about on Tuesday?
So
that process of following the start solutions to the target solutions is called path tracking.
I see.
Yeah, so we can look a little bit deeper. So here's this result. You can ask for the first thing. Okay, it's a path result. Tells us a lot of information. Tells us whether or not it thinks it was successful, what the solution is, what the accuracy is, what the residual is, what the condition number of the Jacobian is, how many steps it took, whether or not it had to go into extended precision, and what the path number is. So that just means it's the first start solution on the list. And we'll talk about most of these aspects later. Any questions? Anything online? I can't see the chat box so well, so if you do have a question online, please unmute yourself and just feel free to interrupt. Okay, great. So this should get you started on solving polynomial systems. Now we're going to go faster. Okay? I want to showcase something it actually can do, and we'll see if I can do this in real time. All right. So we talked about polynomial systems, and we talked about the varieties that they cut out. A variety cut out by a single polynomial is called a hypersurface. Okay. I am going to be interested in cubic hypersurfaces in three-dimensional space. So solutions to polynomials of degree 3 in x, y, and z. So there is a theorem by Salmon, the salmon that my computer is named after, that if you give me just a random cubic surface in 3 dimensions, it will have 27 lines contained in it. I want to do that on a computer. Okay, so here are the monomials associated to a cubic in 3 variables. I don't think I've missed any. Feel free to correct me. It's for me to look at while I'm coding. Okay? And so let's get the format of a generic cubic into Julia here. Okay. Actually, let me do one more thing before we do that. So that's just a teaser, I guess. I want to show you one more way you're going to use Julia and homotopy continuation a lot in this course. And that's for parameterized polynomial systems. This is everybody's favorite one. But now that we have 2 different types of variables, we're going to have to tell it what the parameters are. It will happily infer what the variables are from that information. But if you want to be extra careful, oops. It expected a vector of variables, but I gave it a variable. So better make it a vector of variables. Okay. This is a random function. The n after random stands for a normal distribution, I believe. I want 3 random complex numbers. Boom. And I want to solve f, where the target parameters is p. Let's see if we can do this. I think so. Yay! Great. Of course, I don't expect any real ones. I'm just putting random complex numbers as coefficients. Right. P big. Here are 100,000 triples of complex numbers. Don't worry, they won't all print out. Okay, that's how you do it. List construction is pretty easy in Julia. Again, this is all recorded. You can pause, you can go back, and I will copy this terminal session. Okay, what I call this? Oh, up, by the way, goes to your history. That's really helpful. And if you start typing and then you start doing up, it will search through your history of commands you've written that start like that. Okay. Great. So S big, solve F, start solutions, start parameters. So now I want to solve 100,000 quadratic equations. I remember how long it took before. Wow.
Yes.
Okay, and this is on Zoom and blah, blah, blah. Let's see if I embarrass myself. Boop, 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 boop. Holy heck. All right. Okay, it's just a quadratic equation. I could, whatever. I can write a function which writes it symbolically. Yeah, but that's not what it's doing. It's doing homotopy continuation on 200,000 paths. Okay, real time on Zoom. Very, very easy polynomials. Okay, time to soup things up. X, Y, and Z. Sorry, Z. If I see Z, I mean Z. F will be, oh, wait, I want parameters for this, right? So I'm gonna overkill my parameters here at 1 to 4. So I would like to do 0 to 3. So maybe this is a example of where I might have liked indexing at 0. We're gonna do this. So Cijk will be the coefficient of x to the I minus 1, y to the j minus 1, and z to the k minus 1. My cubic is going to be nothing. for I from 0 to 3, for I in 0 to 3, for j in. Now I don't want I plus j to be any bigger than 3. Minus I. What am I doing? I is scrolling from 0 to 3. That's the coefficient of, that's the exponent of x. Y will be going from 0 to 3 minus I. That will be the exponent of y. And then k will go from 0 to 3 minus I minus j. Okay. Dang. Oh, f is not what I called the cubic. I called the cubic. Thank you. Boom, yay. So C111 is interpreted as C000, but I'm not indexing at 0. And so now I have a general cubic. Okay. A little scrappy with this iterated for loop, a slicker coder than I could write this better. You have a question?
I was wondering, how do you go down to 1? This was the first time I'm actually using Julia. How do you make it go down 1? Because like I'm able to say shift enter. Well, no.
Oh, just enter will go to a new input line.
Yes, how do you add?
However, if you have started something like for I in blah, 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 it will know that you are not done yet. So when you hit enter, it will not go to a new input until you've put sufficiently many ends afterward. Yeah, so it's a bit tricky to do this, right? Because we're also like in the term. So yeah. Okay. Does anybody want to tell me a description of lines in 3-dimensional space? Say again?
AX plus BY plus CZ plus D, but that's thing, right?
That would be a hyperplane. Yeah, so I could write down the intersection of 2 random hyperplanes, and that would be a random line. Great. I don't want to do that. I want to use this thing about intersecting parameterized things and implicit things. How do I parameterize a line?
Direction ratios, I guess.
Direction and point.
So direction ratios like I don't know, A over A minus X over A minus something.
Let's not hurt ourselves too much. Let's see what we can do. I want my line parameter to be t. I want the starting point, so at t equals 0 of my line, I wanna be maybe let's say v, and then my direction is gonna be u. Well, okay, so L will be vi plus t times ui for I in 1 to 3. Okay, so that's the parameterization, where v and u are, you know, some actual numbers, and then t is the parameterizing variable, yeah? Can I do this? No. So now I want to do a substitution. How do I do it? I put something there, and then I put arrows like that, possibly in a vector to make things work. So subs cubic xyz goes to what? L. Substituted cubic. Awesome. So if somebody gives me a line and gives me a cubic, that means you've given me the CIJKs, you've given me the VIs, and you've given me the UIs. The only thing left here is a T. And indeed, if I expand this out, By the way, ANS is the previous output. I will get a polynomial in T, where T is never raised to a power higher than 3. So it's a cubic polynomial in T, and its roots are the intersection points of that line with that cubic. Russell.
Yeah, could you go off over the equation of the line that you wrote?
Yeah,
for
absolutely.
separation of points?
There we go, L.
Yeah.
And we
So
got
we
a
can-
chat question too, so. Yes, thank you. Orthogonal vector of a hyperplane. Yes, plus a translation vector, indeed. Yeah, so if you're following along and you get stuck, I suggest just returning via the YouTube video later.
We want to substitute. So sums.
Okay. Yeah, so we did this substitute, the cubic, the list of things we want to substitute, and what their values are. And so I'm just gonna move on here. All right. All right, so now the roots of this polynomial of degree 3 in the single variable t are the intersection points of the cubic and the line. So what would it mean in terms of this polynomial that's written down for the line to be contained in the cubic? Well, it would have to have infinitely many solutions, which would mean that this polynomial I'm looking at would have to be the 0 polynomial, which would mean the constant term would have to be 0, and the linear term would have to be 0, and the quadratic term would have to be 0, and the cubic term would have to be 0. That would tell me that for any t value, I get an intersection point. In other words, the line is contained in the cubic. If it works. Beautiful. So I asked for the coefficients of this substituted cubic in terms of t. I gave it a name, and I got a vector of 4 elements. The coefficient of 1, the coefficient of t, t squared, and t cubed. These are my equations. The variables, so that's what I'm solving for, are the v's and the u's. vcat is how to combine lists. The parameters are the c's. And this is the embarrassing part. That's good. There we go. Okay, don't worry about it. We're just gonna finish this up. Okay. 4 polynomials, 6 variables, 64 parameters. Okay, so that's overkill on the parameters, but maybe that's fine. No, okay. Yeah, this is fine for now. More parameters isn't gonna hurt anybody. What is gonna hurt us is that we have only 4 equations and 6 variables. We don't have a square system. Okay. And the reason is how we're representing lines. There's not a one-to-one correspondence between lines and this way that we're representing them. If somebody gives me a line, there's lots of ways to choose a starting point and a direction vector. Right? And we haven't made any specifications about that. And so if there is a line, which is a solution to this system, we're gonna have infinitely many solutions in the variables u and v. So we're just gonna add some more equations. If you're interested in how to do all of this, then you can choose this as your project. But basically, I'm going to represent a line by saying that the starting point is where it intersects the z equals 0 axis, which is most lines. We're missing some lines. And then the first coordinate of the direction vector is just 1. F. Okay, so now, moment of truth. let's solve f for the target parameters, which is just some random complex numbers. We need 64 of them. There we go. Boom. 27.
We want that 27 lines.
Yep. So each one of these solutions corresponds to a line on the cubic surface corresponding to this random complex vector. It has tracked 45 paths, which is a much smaller number than the analog of the start systems that we were talking about before. In fact, if you look at these 6 equations, looks like they have what degrees? Degree 3. Yeah, so a zoo number. Yeah, no. Okay, never mind. It doesn't work for parameterized polynomial systems. Okay, that's okay. Great. So yeah, it can solve it. Great. And so let's do what we did before. Solve for let's do a P1. Solve for a single parameter value. And then solve like 1,000 instances of this or something. Right, it's a much bigger system than the quadratic equation story. So let's do it. Great. P big equals random. Let's do floating point. So let's do like real parameters too. 1,000 maybe. Okay, and then this command ends up being exactly the same as what I had before. Boom. There we go. Pretty good. Each one of these instances, it's tracking 27 paths. And here we are. And now we're gonna take a look. Okay. It's 3 real, 7 real, 7 real. Let's see how many real ones we ever get, right? So maybe like, so one instance looks like that. The solutions look like that. I can ask for the number of real ones, and I get that. So that is a list of the real counts for each one. You'll have to do something like this on your homework for the quadratic equation, by the way. So it looks like we get a lot of 3s and 7s. Reality bucket. Great. Count. The number of times we get 3 in the reality bucket. So out of 1,756 times, we found 3 real solutions. Okay, let's actually just count how many times we get I. So I goes from 0 to 27. And let's print line that answer. Interesting. Does anybody see a problem with this? Uh-oh, plug your computer in. Okay, anybody looking at this should see a problem. I am solving a polynomial system over the real numbers. And sometimes I get 2 real solutions, and sometimes I get 3 real solutions. That's a problem. My non-real solutions need to come in complex conjugate pairs. What we are seeing here is a wrong answer. In fact, yeah, this 2 is wrong. You should never get an even number of real lines on the cubic. The parity should always be odd. This is wrong. also. Why did this happen? So this happened because of some tolerances that are numerically set in this process that maybe weren't tight enough or too tight. And so paths were lost. Perhaps like one real solution was lost. So this is a feature of dealing with numerical calculations, okay? If I'm worried about it, you can certify it. And if we tried to certify these things, it would only certify 26 solutions and 2 of them would be real or something, which would indicate to us that we've missed one real solution, okay? Very big, I don't know. It's a cool theorem that you can only get 3, 7, 15, or 27 real lines on a cubic surface. Not the easiest thing to prove, especially if you're not, into all this enumerative geometry and real algebraic geometry. But here, we can actually suspect that that might be a theorem just from an explicit calculation. And this is a big way in which numerical algebraic geometry is useful in research. You can do large computer experiments, subject to the consideration that you might have wrong answers. But if you're really concerned, you can do certification. And you can see patterns. And you can predict theorems. And you can prove things. And you can solve systems with lots of solutions. Okay, 27, by the way, is not a lot for systems like this. For like software systems like this. We get into millions. Okay. So that is Crash Course in Julia. I'll copy this all into a big file that I'll host on the web page. So thank you very much. I'm going to stop the sharing. I'm going to stop the recording, and we'll take offline questions.